In this lesson, we're going to get introduced to two formulas that you can use to find missing sides and missing angles in triangles. They are called the law of sines and the law of cosines. And we're going to prove those later, so I just want you to get comfortable with the formula for today. They can actually be used for all triangles, not just right triangles. When we use SOHCAHTOA, we assume that we have a hypotenuse, which means that we have a right triangle. There is a convention, that is a customary way to do things in triangles in trigonometry, and that is, if I look at vertex A with a capital A, then lowercase a would be the length of the side opposite that. Same with uppercase B, we'll have the length of side B opposite that angle. The law of sines stated is that the sine of angle A divided by A is equal to the sine of angle B divided by the length of side B, which is also equal to the sine of angle C over the length of side C. Now that looks like a funny equation because we have two equal signs, so I want you to know that we're actually in practice only going to use two of these things at a time, which will perform a proportion, and we can solve that by cross-multiplying. When we use the law of cosines, that's going to look a lot like the Pythagorean theorem, c squared is equal to a squared plus b squared, but since it's not a right triangle, we have to correct that with a minus 2 times a times b times the cosine of angle C. Observations about the structure of this: side C sits all by itself on one side, squared, and angle C is the angle that we are taking the cosine of. There are variations on the law of cosines where we put another angle and another side on opposite sides of the equation. So we just rearrange the equation. It's valid for all permutations of that, depending upon which side you want to isolate and which angle's given. So what we're going to do first of all here is we're going to set up either the law of sines or the law of cosines as an equation that could be solved for the unknown side or angle. And we're not going to solve the equations, I just want you to get used to the formula. So I'm going to draw a triangle ABC. It doesn't matter in what orientation you draw it. It just matters that we care what the sides are that are opposite angle A and angle B and angle C and so on. So we are given some things which I'm going to mark in my diagram. The measure of angle B is 64 degrees. The measure of side B is 9. And the measure of angle C is 38 degrees. And we are looking for the measure of side A, which is opposite angle A. Once we have all that set up, then we can take a look at the law of sines and law of cosines. Let's take another gaze at those. And let's observe that in the law of sines, which I will highlight here, law of sines, that's not doing a good job of highlighting. Well, in the law of sines, we have a proportion, that part that I have boxed in there right there. I need to have, in order to write a proportion, two sides and two angles in that proportion. So if I have two sides and two angles, I will be using the law of sines. Well, that's our setup for example 1a. We do have two sides and two angles. So I'm going to start writing the law of sines. The law of sines states that sine of 64 degrees divided by the measure of the side opposite it, which would be 9, is equal to, and now I need another pair of opposite side and opposite angle. You'll notice that the given angle, 38, is not opposite the side that we are trying to find. So I'm going to do the easiest thing that I can when solving a triangle, and that is I'm going to use my two given angles to find the third angle, because we do know that the sum of the angles is 180. So the measure of angle A is equal to 180 minus 64 minus 38, and that will be 102 subtracted from 180, which would give us 78 degrees. So the measure of angle A is computed 78 degrees, even though it wasn't given. And now that's opposite side A, so we can write the other side of the proportion, which is sine of 78 degrees divided by A. And there's our proportion that we could cross multiply and solve for a. All right, now another observation. Let's take a quick look at the law of cosines. In the law of cosines, I have a side squared equals another side squared plus another side squared minus 2 times the product of the sides times the cosine of an angle. So in the law of cosines, I'll be given 3 sides and 1 angle to work with to write an equation. So that's actually what's going to happen in this next example. I'm going to draw my triangle XYZ. And by the way, your triangles don't have to be to scale. All of mine are going to look like equilateral triangles. It doesn't matter. So angle Y's measure is 127. Side X, opposite angle X, measures 16 units long. Side Z, opposite angle Z, measures 11 units long. And we are looking for the measure of side Y. So this looks like a 3 sides, 1 angle combination. And when you write the law of cosines, it's important that we start with the correct side isolated by itself on one side. Just like the hypotenuse is by itself in the Pythagorean theorem, in the law of cosines, the side that I want to write by itself is the one that corresponds to the angle opposite. So y squared is equal to 11 squared plus 16 squared minus 2 times 11 times 16 times the cosine of that opposite angle from y, which is 127 degrees. And there is the equation that we could solve for y. All right, let's check out C. In C, we are given triangle BAM. Side B's length is 7, side A's length is 8, side M's length is 10, and we are looking for the measure of angle A. This looks like a 3 sides, 1 angle setup. That's the law of cosines. The squared side that we start with, all by itself on one side of the equation, is 8 since it's opposite the angle in question. So 8 squared is equal to 10 squared plus 7 squared. It's going to start like the Pythagorean theorem, minus 2 times 10 times 7 times the cosine of angle A. And there's the equation that we could solve for the measure of angle A. All right, let's move on to triangle JNK. Measure of angle J is 25 degrees. The measure of side K is 9. The measure of side J is 6. And we are looking for the measure of angle K. This is a 2 sides, 2 angles situation, so we can write a proportion using the law of sines. Sine of angle K divided by the length of the side opposite equals the sine of angle J, which is 25 degrees, so I'll just write in 25 there, over the length of the side opposite, so over 6. All right, let's try E. Or rather, why don't you try E on your own and pause the video while we do this. Here's the equation that results from example E. Notice that we had to find the third angle first to make sure that we had an angle that was opposite side G, which needed to be in the proportion. All right, now try H on your own. Pause the video while you do this. For this exercise, the law of cosines was necessary since we had 3 sides involved in the equation and 1 angle. Q had to be by itself on one side since the angle involved is the angle opposite Q. All right, now we're going to actually solve some proportions that have already been set up for us. These would be the law of sines. And we need to keep in mind that we are solving for angles in a triangle. Every angle in a triangle will be somewhere between 0 and 180 degrees, but not greater than 180 degrees because all 3 angles in a triangle must add up to 180. So a suggestion about how to start by cross multiplying. So A times the sine of 135 degrees is equal to 6 times the sine of 30 degrees. Now we're going to have to do this without a calculator, so we're going to have to make some sketches of some familiar angles. So let's start with 135 degrees. 135 degrees is an obtuse angle, so when drawn in standard position, it will terminate in quadrant 2. And I'm going to zoom in on this drawings to make sure that it's visible to you. When we sketch in a reference triangle, the reference angle will be 45 degrees. And remember that in a 45-45 right triangle, we have sides of 1, 1, and the hypotenuse is the square root of 2. But since we're in quadrant 1, that adjacent side will be negative. So we're going to need to find the the sine of 135 degrees. That'll be opposite over hypotenuse, which is 1 over the square root of 2. But we're actually going to write that in rationalized form, the square root of 2 divided by 2. And then on the right hand side, we need the sine of 30. We'll need to make a quick sketch of a 30-degree angle. That's an acute angle, so that's going to terminate in quadrant 1 when drawn in standard position. And 30-degree angle, we can draw in a reference triangle. And in a 30-degree angle, the opposite side from the 30 degrees is 1. And the adjacent side square root of 3, and the hypotenuse 2. So that means that the sine is opposite over hypotenuse, which is 1/2. Let's clean up what we have on both sides of the equation. A times the square root of 2 over 2 is a times the square root of 2 over 2. 6 times 1/2 is 3. Now I'm going to clear the fractions by multiplying both sides by 2. So a times the square root of 2 is equal to 6. And now we need to undo that multiplication by the square root of 2. So a is the 6 divided by the square root of 2, which can be and should be rationalized. That is, we're going to rationalize the denominator, make the denominator a whole number. And that'll give us 6 times the square root of 2 divided by 2, which simplifies to 3 times the square root of 2. All right, let's move on to another proportion. In B, we have this proportion, but before we start evaluating those trig functions, I want to cross multiply. So 2 times the square root of 3 times the sine of angle A is equal to 2 times the sine of 60 degrees. Now we have a sine of 60 degrees that will need to be evaluated. When drawn in standard position, an angle with 60 degrees will terminate in quadrant 1. Let's draw in our reference triangle. And that will have sides of 1, square root of 3, and 2. So now let's clean up some things. 2 times the square root of 3 times the sine of angle A is equal to 2 times the sine of 60 degrees, which would be the square root of 3 divided by 2. And you'll notice that on the right side of this equation, we can do some simplifying or some cleaning up. 2 times the square root of 3 divided by 2 is the square root of 3. And now we want to find the value of angle A. Well, we have to first divide by 2 times the square root of 3 in order to get the sine of A by itself on one side of the equation. So the square root of 3 divided by 2 times the square root of 3. Let's grab that handy-dandy cancellation pen. Cancel those common factors, leaving 1. So sine of angle A is equal to 1/2. Now let's bear something in mind. We're looking for the angle that has a sine equal to 1/2. You'll remember from Unit 1 that this may have multiple solutions. Bear in mind that we are only looking for angles that fall in the 0 to 180 degree range. That's going to be angles when drawn in standard position that fall into quadrants 1 and 2. Now we remember the mnemonic for this, that whether sine is positive or negative in which quadrants, and in quadrant 1 all functions are positive, so when sine of A is equal to 1/2 we should get a quadrant 1 solution. And then in quadrant 2, sine is positive still, and so we should get a quadrant 2 solution as well. Quadrants 1 and 2 are all the angles from 0 to 180 degrees, so that should cover us. We're not going to look elsewhere. And the reason, again, that we're looking only from 0 to 180 degrees is that these angles are angles in a triangle, and any angle in a triangle may not be any bigger than 180 degrees. So I'm going to draw a quadrant 1 triangle. And I'm going to draw one that has an opposite over hypotenuse equal to 1/2. You'll recognize that as the ever popular 30, 60, 90 triangle. And so that means one of our solutions is 30 degrees. We'll also have a quadrant 2 solution. So this is our quadrant 1 solution. Let's draw the quadrant 2 solution. The quadrant 2 solution will have a reference triangle that will look very similar. It's going to have a 30-degree angle in that reference triangle, and opposite and hypotenuse will still be 1 and 2. Now, the difference here is that our adjacent side will be negative, but that won't make any difference for the sine of angle A. But remember, 30 degrees is not the angle that we're looking for. We're looking for the angle that starts at the positive x-axis and rotates to the terminal side, and that will be the supplement of that 30-degree angle, or 150. So sometimes I'm going to say sine is ambiguous. That is, if the sine of angle A is 1/2, there are actually two solutions. That means that theta is either equal to 30 degrees or theta is equal to 150 degrees, and we do need to give both solutions. One thing that you will notice about this pair of quadrant 1, quadrant 2 solutions is if we have those two solutions in those quadrants, they will be supplementary. So if we find the solution in quadrant 1, then we just need to find the supplement to find the second solution. Now that's only valid for sine. For cosine, different story. Speaking of cosine, here's an equation that looks a lot like the law of cosines. So we can solve for A here, but I'm going to just clean up what's on the right side of this equation. So 16 plus 4 is 20. I'm not going to subtract 16 because 16 will actually be multiplied by something, and that something is the cosine of 120 degrees. Let's make a quick sketch of what 120 degrees looks like. 120 degrees is an angle that rotates past 90, so into quadrant 2. And so if this is 120 degrees, inside our reference triangle, the reference angle will be 60 degrees. That gives us an adjacent side of 1, opposite square root of 3, hypotenuse of 2. Oh yes, but remember the adjacent side is pointing to the left or directed to the left, so it has a negative side length. And so adjacent over hypotenuse will be negative 1/2. So now we just need to do some multiplication. Negative 16 times negative 1/2 is positive 8. And so a squared is equal to 28, which means that a is the square root of 28, or a is in simplified form 2 times the square root of 7. Notice that we're only picking the positive side length because, very much like our consideration of angles, we are considering sides in a triangle, not sides in reference triangles that we're drawing. So we're not talking about directed sides, we're just talking about lengths of sides. All right, let's check out another situation with law of cosines. 3 is equal to 1 plus 4 minus 4 times the cosine of angle A. This time we'll solve for the angle measure. So I'm going to clean up some things here. And I want you to be careful. We cannot subtract 5 minus 4 before we multiply by cosine of angle A. So I want you to think of this as an equation not unlike 3 is equal to 5 minus 4 times x. We would start solving that equation by subtracting 5, so that's what we're going to do here. 3 minus 5 is negative 2, equals negative 4 times the cosine of angle A. Now we need to divide by negative 4, and negative 2 over negative 4 is 1/2. So now cosine of angle A is 1/2. Now remember, we're still only looking in quadrants 1 and 2. Cosine is a positive number, which means we should be looking in quadrant 1 because all functions are positive in quadrant 1. In quadrant 2, sine is positive, which means cosine is not. And so if cosine is not, let's not look in quadrant 2. So there's no ambiguity about a cosine equation when solving for triangles' angles. That is to say, if we're only looking for angles between 0 and 180 and cosine is positive, their only result should be an angle that's in between 0 and 90 degrees. So I will make a quadrant 1 sketch, and we want to draw an angle that has a cosine of 1/2. That is adjacent over hypotenuse, and that means our opposite side is the square root of 3. That's a 60-degree angle. So that means that the measure of angle A is 60 degrees. There's only one solution to this equation. No ambiguity about the law of cosines. All right, let's check out some others as well. Sine of 120 divided by 10 equals sine of 30 divided by b. Again, we can cross multiply. So b times the sine of 120 degrees is equal to 10 times the sine of 30 degrees. And I'm going to need to make a sketch for 120 degrees. If we draw 120 degrees in standard position, when we get the reference angle, it will be 60 degrees. Let's draw a triangle associated with that. Adjacent, -1, hypotenuse 2, and opposite square root of 3. So that means that the sine of 120 degrees is the square root of 3 over 2. Sine is positive in quadrant 2. And now we need to draw a 30-degree angle, so I'll draw a sketch of that. 30-degree angle terminates in quadrant 1. And so we can draw a reference triangle there as well. Opposite side is 1, hypotenuse 2, and adjacent side square root of 3. That means that the sine of 30 degrees is 1/2. All right, let's clean up what we have here. B times the square root of 3 over 2 is equal to 10 times 1/2, which is 5. I can certainly multiply both sides by 2. And now we need to undo the multiplication by the square root of 3. That'll be undone by division. 10 divided by the square root of 3. And of course, we would never leave that square root in the denominator without simplifying or rationalizing the denominator. So that will give us 10 times the square root of 3 divided by 3 is our final value for b in rationalized form. All right, let's try another law of sine setup. Sine of 45 degrees over 2 equals sine of angle A divided by the square root of 2. And this time we'll be solving for an angle. Let's cross multiply. 2 times the sine of angle A is equal to the square root of 2 times the sine of 45 degrees. All right, I'm going to draw a quick 45-degree angle. That'll terminate in quadrant 1. Drawing the reference triangle, it'll have sides of 1, 1, and the square root of 2. So now when I bring my equation down to the next line, 2 times the sine of angle A is equal to the square root of 2 times the sine of 45 degrees. The sine of 45 degrees is opposite over hypotenuse, and I'm not going to rationalize it this time, and the reason I'm not going to is we have the square root of 2 times 1 divided by the square root of 2, or reciprocals. So when we multiply those two reciprocals together, we're going to get 1. And then sine of angle A is equal to 1/2. Now, we know that if we're looking for angles that are between 0 and 180, all functions are positive in quadrant 1. Only sine is positive in quadrant 2. but we're looking for where sine is positive, so it looks like we're going to have two solutions. In quadrant 1, we can draw a picture. Sine of angle A is a half, and opposite over hypotenuse will be a half. That's going to be a 30-degree reference angle. So the measure of angle A is 30 degrees, or, and if you remember our technique for finding the second quadrant solution, if we already know the first one, is that they are supplements to one another. So the other solution is sine of 150 is equal to 1/2, or 150 degrees is another possible angle measure there. All right, let's try another couple. B squared is equal to 36 plus 4, which is 40, minus 24 times the cosine of 60. So we need to evaluate the cosine of 60 degrees. 60 degrees is an angle that terminates in the first quadrant. Oops, and it will have an adjacent side of 1, opposite square root of 3, and hypotenuse of 2. So cosine of 60 degrees is adjacent over hypotenuse, or 1/2. So b squared is equal to 40 minus 24 times a half is 12. B squared is 28. That means that b is the square root of 28, or simplifying 2 times the square root of 7. Same result we got in a previous example with some different numbers, just happened to work out the same. And one last law of cosines example. Let's do a little bit of the arithmetic here. 1 plus 2 is 3. And remember, we cannot simplify what we have here. You need to make sure that we know that 2 times the square root of 2, or rather negative 2 times the square root of 2, is the coefficient of cosine b. So in order to uncover cosine b, or solve for cosine b, we need to subtract 5 first. And then divide through by negative 2 times the square root of 2. And that gives us cosine of angle B is equal to negative 1 over the square root of 2. I'm not going to rationalize that because I think it will be easier in unrationalized form to draw our reference triangle. If we are looking for an angle that's between 0 and 180, we're only looking in quadrants 1 and 2. And if cosine is negative, that must be a quadrant 2 angle. So quadrant 2 is the angle, quadrant 2 is the place where we want to look for our solution. So I'm going to draw a quick quadrant 2 picture. And our angle rotates from the positive x-axis, and we want to have a 45-45 right triangle, because you're going to recognize those sides. Our adjacent side should be negative 1, hypotenuse square root of 2. That's a 45-45 right triangle, and that must mean that the angle that we're looking for is the angle 135 degrees. So the measure of angle B is 135 degrees. No ambiguity about solving for an angle with a cosine equation. There's only one solution. Again, we're not looking in any other quadrants. For instance, quadrant 3 would be a place to look for a solution if cosine were negative, but quadrant 3 angles are bigger than 180 degrees, and these are considered to be angles in a triangle, so bigger than 180 degrees is not an option. Okay, we're going to skip the try these. You can try them if you want. The last thing that we're going to do here is we're going to label some given information. When we solve an entire triangle, we're going to find more than just one missing side or angle. We're going to find actually all of the missing sides based on givens that are 3 of its sides, or 2 sides and an angle, or some combination of 3 things that will be given. They're going to determine which formula to use by studying the pattern of the given measures. So you'll recognize all of these patterns from geometry. Side, side, side would be if 3 sides were given. Side, angle, side, angle, side, angle, 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 side, and SSA. SSA was something we were not told to use in geometry. In fact, we were told we shouldn't use it, and that was for the reason that we cannot prove two triangles congruent based on SSA congruence. It turns out that we can actually utilize the SSA case in trigonometry, but we actually may get more than one solution, so it is ambiguous. And let's take a look at example 3a. In this triangle, side A measures 3, that's going to be opposite vertex A. Side B measures 5, that's opposite vertex B. And measure of angle C is 20 degrees. Notice that that angle is formed by the two sides, or the angle is in between the two sides. That means that this pattern of givens is a side angle side situation. In B, we have side A measuring 7, and measure of angle A is 40 degrees. Measure of angle C is 70 degrees. Notice that this particular side is not the side that's between the two angles. The side that's between the two angles is the one that I'm highlighting right now. So, in this case, it's not angle side angle, it's angle angle side as our pattern of givens. In C, side A is 7, side B is 8, and side C is 10. There are 3 sides given, so side, side, side is the pattern of givens. In D, side A measures 6, side C measures 9, and angle C measures 30 degrees. Notice that the two sides do not have the 30-degree angle right in the middle. The two sides meet at angle B, so if angle B were given, this would be side angle side, but since the angle is not in the middle, this is an SSA situation. Side side angle because the angle is not in the middle. In E, we have measure of side B is 3, measure of angle A is 20 degrees, and measure of angle C is 100 degrees. Notice this time that the side that's given is right in between those two angles, and so in that situation this is an angle side angle type of pattern of givens. Part F actually matches the previous example, so its answer is actually the same. Surprising. Alright, now we're going to involve our calculators just a little bit, but we're going to actually do the bulk of the work before utilizing the calculator. So we're going to use the inverse sine to solve for p, and then we're going to find out something else about our solution. So we cross multiply and we get 6 times the sine of angle p is equal to 10 times the sine of 35 degrees. What we're going to do is we're going to get an exact form solution, or rather a calculator ready form, and then put it in at the last minute. We're not going to do anything on the calculator until we get to our answer. So I need to solve for p, so I need to undo that times 6. So now I have 10 times the sine of 35 degrees over 6. And I know I can reduce that, but since this is a calculator problem, I don't really care. I know that next step I want to do is I want to isolate angle P. So I want to undo the sine, and we can undo the sine or solve for the measure of angle P by finding the inverse sine of the other side. So the inverse sine of 10 times the sine of 35 degrees over 6. There's our exact form, or calculator ready form. Now I'm going to bring up my calculator, and if you're in Scratchpad, you're going to want to start with an inverse sine. So inverse sine is in your trig menu. It's that second thing right there. Inside the parentheses, use Control Divide to get that horizontal fraction bar, and then enter the numerator. 10 times the sine of 35 degrees divided by 6, and press enter. That'll give us 72.933. But we remember that sine is not only positive in quadrant 1, it's also positive in quadrant 2. So that means we're going to have a second quadrant solution. So our second solution can be found by taking 180 degrees and subtracting that first solution. But what I'm going to encourage you to do is to use your calculator's answer feature to do that subtraction. Don't retype. So just write 180 degrees minus, and then the answer, which you can find by control and the negative sign. Or you can just type the letters A and S and it'll do the same thing. And that will give us 107 degrees, 0.067. Remember, we're going to typically round to 3 decimal places. If you want to set your calculator on fixed 3, you can. If you're taking another course where you're using your calculator, you may want to just leave your calculator on float. Last example, we're using the inverse sine to find the measure of angle V here. So another law of sines type of situation. And we have 4 times the sine of angle V, if we cross multiply, equals 7 times the sine of 35 degrees. We're going to divide by 4. So sine of angle V is 7 times the sine of 35 degrees divided by 4. And then we can find measure of angle V by taking an inverse sine. And let's bring up our calculator. So I want to type the inverse sine. It's in our trig menu. And control divide for a fraction. So 7 times the sine of 35 degrees divided by 4. And that's going to produce an undefined result. So that's undefined. And what I kind of want to make sure that we understand is, why did we get that result? Why was there no solution for this equation? And in order to help us understand that, what I want to do is just type what's on the inside of the inverse sine. So on the inside of the inverse sine is a fraction 7 times the sine of 35 degrees divided by 4. And that number is equal to about 1.004. Is that correct to the, yeah, 1.004-ish, okay? And that was what our sine of angle V was equal to, right? Now let's remember something about sine of angle V. That would be the opposite over the hypotenuse. In a fraction where we have the opposite over the hypotenuse, if we get a number that's larger than 1 for that ratio, that means that the opposite would be larger than the hypotenuse. And we know that that's not possible in a right triangle. So the sine ratio gives us that opposite over hypotenuse. If sine's bigger than 1, that causes a problem. Sine is allowed to be equal to 1 because opposite and hypotenuse can have the same length for quadrantal angles, if you remember our quadrantal angles, but not any larger. The opposite must be the same or smaller than the hypotenuse in size. And that's it for the lesson.